you get all this data from the Earth observation satellites and the Copernicus program, and you make it available to the world.
Absolutely, that data is available as soon as it comes onto the ground. It's available to everyone.
And that's without any charge?
Yes. Yeah, because we understand that this is helping humanity. So if you put a charge on that, then you're doing it for profit. You're not helping humanity. So no, this information, and all of our satellites, all the data from all ESA satellites is available free of charge.
Episode 106, ESA's new science missions. The European Space Agency's Paul McNamara was studying low-frequency gravitational waves just before they were discovered in 2015. Now he is the Astronomy and Astrophysics Coordinator for the European Space Agency. In this interview, recorded in Athens during COSPAR 2022, he speaks about some of the exciting science missions that ESA will be launching later this decade. These missions include JUICE, Jupiter Icy Moon Explorer, Euclid, to explore dark matter and dark energy, Plato, the next generation planet hunting mission, Ariel, a UK-led mission to explore the atmospheres of exoplanets. He also talks about ESA's publicly available resources, especially useful to science educators: Planetary Science Archive and ESA Sky. They are available to anyone, in or outside Europe, and without charge. Links are available on this episode's webpage.
Paul McNamara, thanks for making the time. You're here at COSPAR 2022 in Athens. You're with ESA. What's the work you do with ESA, and how long have you been there?
So I've started working in ESA in 2005, so actually almost the 1st of October 2005, so almost 17 years I've been with ESA. And in that time, I originally was the project scientist of a mission called LISA Pathfinder, which was a technology demonstration mission for the future large gravitational wave antenna LISA.
Right.
So we launched Pathfinder in 2015, and that operated to about 2017. And then after that, I became the study scientist of LISA, which is a laser interferometer space antenna. So that's a large gravitational wave observatory. I then moved from LISA to, it's called coordination. So I'm now the astronomy and astrophysics coordinator. So that's dealing with our advisory structure in the astronomy side, but also with some of our member states related to all of our astronomy missions.
Tell me how you got interested. Well, was space already always on the cards for you when you were studying?
Not really. Actually, I went to university to study physics.
In Glasgow?
So I went to the University of Glasgow to study physics, and in my sort of your induction day when you meet your advisor of studies, I had planned to do the standards, as most school kids do, maths, physics and chemistry. And he advised me, why are you doing chemistry? Why don't you think of astronomy? It's more fun. And I thought, okay, at that time I was young, didn't have any care in the world, so I said, okay, I'll do astronomy. And I absolutely loved it. And that got me into the world of astronomy, so I did a double major, physics and astronomy. And then for my PhD, I was very fortunate I was in Glasgow because the LISA project, the one that I've worked at ESA, it was really at the very, very early stages. People thinking about it, a bunch of scientists getting together at a conference with a napkin at a dinner table, picking up with this concept of a mission called LISA. And that was around about the early 90s, and I started my PhD in 94. So I think I actually was the first PhD student to work on LISA. And that got me involved in it, and I loved it. And what I loved about gravitational waves in those days, I said in those days, things have changed recently, is that you're involved in every aspect. So you had to do the building of the hardware, the analysis of the data, and also the theory side of it. So you're also looking at what are gravitational waves, the general relativity, the sources. And to me that was a perfect combination of work that I wanted to do. I said in the old days, because now we've discovered gravitational waves, back in those days I was told by several people, eminent professors, that I was completely wasting my time.
Right.
Because gravitational waves, first of all, they don't exist. It's a mathematical anomaly. Secondly, if they do exist, you won't be able to find them. And if you could find them, you might be able to find them on Earth, because you can tweak things, but in space, forget it, there's no chance. But again, I was young and I was naive, and I thought this is good fun, and I did it because it was good fun, not because of what was going to happen in the future. And it was the best decision I ever made. And so I've had a great life working on LISA, space-based gravitational waves, and now branching out to all different forms of astronomy. That's been a great place.
And that's really the core excitement of astronomy in space, that some things which were impossible at some stage are now, quite in recent history, are now real. And with the launch of James Webb particularly, it's incredible that that's going to be already providing some incredible science.
Yeah.
So we're going to talk about many of the science projects. Well, that's the thing about ESA. It's quite a large organisation. It has so many feet in so many pots, and so there's science, space, solar system exploration, human space flight, and it involves collaboration with many other countries and space agencies. So let's just start off with human space flight. European Space Agency has always been been making a large contribution to the ISS. Are there currently any ESA astronauts on board the ISS?
We have Samantha Cristoforetti, who's up there just now, and it's very timely. She was doing her first ever spacewalk yesterday.
Yesterday.
So I did see some social media with Samantha outside the space station, so that's phenomenal to see.
Yeah.
And we have an astronaut program. We're just selecting new astronauts at the moment. I don't know the details. I work in space science rather than that, but it's very exciting.
And Tim Peake, he flew aboard the ISS once. He's been up there once. Is he likely to go aboard again?
I don't know the details, I'm sorry. Yeah, when he was up there, it was just, looking at the UK press, what happens with the astronauts, the press of the country the astronaut comes from, it's just amazing. Yeah. And Tim, to me, he completely changed people's attitude to space in the UK. I had my parents and, great aunts and things contacting me to ask about space because they seen that Tim Peake was on the space station and wanted to know more about it, so it was phenomenal. And I would love to see Tim going back, but I don't know the details of that.
Well, last time I was aware, he was working towards a second flight, but things changed in this field quite dramatically. So watch this space. But another big ticket item that ESA works on is and collaborates with NASA on is the Artemis project. Presumably that's still in full flow, and Artemis is supposed to be making a launch this year.
I'm sorry, I've got to admit, I just don't know the details of that.
Right.
So.
But Artemis is something that European Space Agency.
Absolutely, we're involved in it. Yes.
Great.
I know there was supposed to be the first launch of the SLS, which is carrying Artemis. That was planned for actually within the next few weeks, as far as I read that yesterday.
No,
So
you do know.
I know that that's happening. I don't know the details of the program, but I know that the SLS is, and I'm looking forward to seeing that because that's going to be massive.
Should be a collaboration which might lead to the first European to the
boots on the moon. It's exciting stuff.
So currently then, which are the active European space missions that you're involved with and which are likely to be providing some scientific insights in the current weeks and months this year?
So we have James Webb. It's a NASA-led mission, but we also have one of the instruments is coming from ESA, and there's also half of one of the instruments also coming from ESA. And the launch was from the Ariel 5 from French Guiana,
which is a European
launcher in the European spaceport in French Guiana. And it was a picture-perfect launch, Christmas Day of last year. It hit its orbit perfectly, which actually they've now said has doubled the lifetime of the mission because they don't have to use the fuel to get to their final orbit. They can use that for operations. So Webb is outstanding. To say it's complicated is putting it, it's been a disservice to the scientists and engineers who've worked on it, because when you see that thing folded up, when I first started working, I used to work at NASA Goddard, and the project manager there at the time had said, under no circumstances shall you have any moving parts on LISA. You have to have anything that moves breaks, so to have no moving parts. And then you see Webb, and it's just everything had to fold up like origami into the fairing, and when it gets up there it all has to fold out, everything's moving and things are coming here and there. Everything worked, and it's just phenomenal to see it. And you see those first images that came out, and that's essentially, you think if you're a photographer, that's the test shots. That's the ones to see that your camera's still working. The science hasn't even started yet, and that's going to just blow our minds when it happens.
And that's really what I was referring to when I was saying that space and astronomy can reveal that kind of excitement and generate that excitement because of really the impossible missions that they set themselves. And then, because it was the same thing with my initial thoughts with James Webb, far too complicated. It won't never work. And a bit like the sky crane for the Martian rovers. They'll never work. But engineers are the new heroes.
Yeah, absolutely. There's some very, very smart people in the world, and you can, like everything, when you're faced with a problem, when your back's to the wall, suddenly you find solutions. And we've seen that for missions all over. You know, you take the classic one, Apollo 13. You know, how do you get a bunch of people in a room, hundreds of thousands of kilometres away from the satellite, and yet find a way to bring it back home safely? It happens all the time. We had one very recently in our case. We had the Integro satellite. So Integro had a problem, I'm guessing now, over a year ago, where its thrusters failed.
Right.
And so you think, okay, thrusters fail, the mission's over. There's nothing you can do about that. But it has reaction wheels, so it can still sort of reorient itself. But what happens is the sunlight pushes the satellite, and the sunlight pushes it away. And so that was over. But what they found is, well, if the sunlight's pushing the satellite this way, well, why don't we just flip it? Then it pushes it back, and flip it. And it's called the Z-flip strategy. And so the Z-flip strategy meant that even though the mission has no longer any thrusters, the death of any satellite, Integral was working perfectly. And it's flawless. And then we had an issue recently when, just after it came through perigee around the Earth, it lost control and started to spin. Completely out of control. And we didn't know what it was. One of the wheels, one of the reaction wheels that kept it stable had lost its, basically lost power, and so it was grounding. So there was 3 hours of life on Integral in the batteries.
3 hours?
3 hours. The engineers immediately shut down the payload. That increased the life to about 7 hours. And then they basically had to figure out what happened. First of all, what went wrong? So when you figure out what went wrong, okay, how do we fix it? And then once we know how to fix it, what commands do we need to upload to the satellite? And then can we get the satellite saved? So we can bring it back to a safe configuration. And that was done within those 7 hours to manage to get the data, analyse the data, figure out what was wrong, find out how to fix it, upload a command, and stabilise the satellite. And that was done within this short, and it's unbelievable that this was done. And that's what can happen. Again, when you're put very smart people in a room and give them an impossible task, quite often find a solution.
And there's no way you can replicate that kind of excitement in an office job, you know.
No,
Space
no, you
and
can't do
astronomy is where...
Excitement is probably a nice word to use. I'm sure stress. I'm sure people lost many years of their life over that 7 hours. But
one of the other very successful, in my eyes, missions has been the ESA's Earth observation, Copernicus and the Sentinel satellites. Just summarise, what does that project do?
So again, that's not really my field. I'm more on the space science side, so I'm not really so much in the details, but we have a complete fleet of satellites in there. We basically have the Sentinels, which are doing a lot of the climate observations. So we've got everything from measuring clouds, salinity, vegetation, so covering every aspect of what you would really want to do, looking at the Earth and the Earth's observation. And we also have a bunch of technology demonstration missions. So not really technology demonstration, but they're creating the new technologies which will be used later. So an example being EOLIS, which is measuring wind speed. So in future Sentinels, you could have this technology, so that not only do you get, you get the whole level all the way down from atmosphere to the ground. So we have this, and I think we're very proud within ESA that we have this Earth observation program, which is providing data to everyone on Earth. And I think it's fair to say we're in Athens at the moment for this conference, and just in a mountain just 16 kilometres away from where we are today, there was a fire at the weekend, and that fire was burnt a few days, very close to the National Observatory of Athens. So it's something which is real, because it's not something in a distant land, it's something which is very close to where we are. It's getting worse. There was a heat wave which hit Western Europe this week. Greece gets it every year, but this week 40 degrees plus in the UK is ridiculous. We have to understand, and we have to do something. And the more information, the more data we have, the more we can then, basically what we have to do, we have to improve our climate models first. And once we know what's happening, then we have to stop it. We have to do something. And I think having this huge wealth of knowledge coming from the Sentinels and the Earth observation satellites is a way to go.
And you highlight, there's two things. First of all, I just want to go back to something you said. You get all this data from the Earth observation satellites and the Copernicus program, and you make it available to the world.
Absolutely, that data is available as soon as it comes onto the ground. It's available to everyone. And
that's without any charge?
Yes. Because we understand that this is helping humanity. So if you put a charge on that, then you're doing it for profit. You're not helping humanity. So no, this information, and all of our satellites, all the data from all ESA satellites is available free of charge.
And that's phenomenal. It's something which is so critical to the future of humanity. And in addition to that, I seem to remember, and I'm sure it's still around and available today, it's not just data in big databases that's made available. There's a whole set of training programs that ESA provides, and anybody can join them to understand how to make use of that data, which I thought was...
Absolutely, yeah. We run programs every year, and within the Science Directorate, we actually have programs where scientists can come to ESA and then work with the experts. So we have the project scientists and the mission operations scientists, so you can work with those people for maybe a few months at a time, a few weeks, months, to have access to the data. So you have the archives are based in Spain, so you can come there and you can work with people who will not only help you how to access the data, but also you've got that wealth of knowledge coming from the whole mission and everything about that mission, which then you can use that to benefit your own science.
I just want to linger for a moment on the significance of what the European Space Agency and other space agencies are doing, because this is quite a critical issue for humanity right now. We seem to have access to the data and the resources in order to understand and appreciate the problem, come up with solutions. But it's still a social and political hurdles that we have to cross. But it's so fortunate, at least from a scientific point of view, that we are in this point, and that gives me hope and optimism.
Yeah, absolutely. And we have one thing we've done in science. We've been building for several years now. It's called ESA Sky. So we have various archives. So every mission has an archive of data. Then we have one we call the Planetary Science Archive. So it has all the planetary data. And now we have one called ESA Sky, which is all the astronomy data. And that has an advantage. We say, I'm interested in this galaxy, and then we can get all the observations of that galaxy from any satellite. You don't have to go in individually. And this has been recognised as being a phenomenal resource to the community, because you can spend hours of your life just playing. You can go there as a scientist or as a guest, and you go as a guest, you can spend your life just clicking on your favourite galaxy, and you can get all this information, all different wavelengths, different observations, spectra. It's phenomenal. But it's been recognised that having a single user interface benefits so much. All the information is available elsewhere, but you just have one website you can go to. And so there are also plans and discussions about, can you do the same for Earth observation science? So we call it the digital twin Earth. So that you can take all of that information, because to create any climate model, it's not enough to only have the vegetation, or only have ocean salinity, or only have wind speed. You need all of that information coming together. So if we have a single user interface to every piece of Earth observation data we have, suddenly you can then start to improve these models. So it's something which we're looking at. It's not actually there yet, but it's something which is that the Director General is very keen to sort of push that forward, to have that available to the world. And I said it's not to any one person, it's fully available to everyone.
But sure, but just to be clear, ESA Sky is something that exists right now.
ESA Sky exists, and anyone who's listened to the podcast, I say if you have a good few hours to spare, please go and have a look at it. If you only have 10 minutes, don't, because you'll miss your next appointment.
A bit like the museums around the world, we can't
Absolutely,
go So what programs, what ESA projects, what are we expecting to happen in the near future in terms of new spacecraft, new missions and launches? So
within again, I can talk about the science program. We have quite a few things coming up. We've got next year we'll have a mission going to Jupiter. It's called JUICE. It's a bit of a unfortunate name. It stands for the Jupiter Icy Moon Explorer. But it will go to, in particular, the Ganymede. So one of the Galilean moons of Jupiter. We want to really start to study these moons, because you have Europa, which is the ocean, the ice planet. So I think it's an ice crust with a liquid ocean underneath. With Ganymede, we feel it's a solid crust, but again with a liquid ocean beneath the crust. So we want to start looking there to say, well, maybe there's vents coming up. We know we've got these hydrothermal vents on Earth where you get life forming in very hostile environments. Maybe the same thing is happening on Ganymede, and maybe there'll be some vent coming off, which we'll be able to see from orbit. So we're not looking for life, we're looking for habitability, things where it could be somewhere. So that's a very exciting one. To go out to Jupiter and start doing these measurements. We then have either next year or the following year will be a mission called Euclid. Now Euclid to me is a phenomenal mission. The universe at the moment, E equals mc squared. So we think for scientists, energy and mass are the same thing. And for the whole universe, we believe about 4% of the universe is made of what we are: protons, neutrons, electrons. So we call it the baryons. About 21% of the universe is dark matter. You know, with any scientist, when you don't understand what it is, it's either black or dark. So we have dark matter. And then about 75% of the universe is dark energy. And we have no idea. So we know that the universe is expanding to a rate where 75% of the energy of the universe is in this dark energy, which we just don't understand. And so Euclid's a mission which is going to start to probe what is dark energy. So that's such an exciting, that's a completely new field. This is not something we've done before. So this is, which I get excited about, and we're having the opportunity to not only do more, you know, James Webb is a phenomenal instrument, but we've had a telescope before. We haven't had something looking at this dark energy.
So Euclid is going to be in Earth orbit?
Euclid will go to L2.
Ah, right.
So it's going to be, and the reason why L2, I should say, is the Sun-Earth Lagrange point number 2. So
where
that's
James Webb is.
Where James Webb is, where Gaia is also out there. And we go there because it's a much more benign environment rather than Earth. So you have a constant solar illumination essentially, and you don't have to worry about Earth shine. So you get more pointing. So those are the 2 missions that are coming up, and then we have some exoplanet missions. So a bit later in the decade, we have Plato, which is be looking for Earth-like exoplanets, which is a transient. So as you know, as a planet passes in front of a star, you get a small dip in the light. So it's a very large field of view. Something like 26 small telescopes covering an enormous fraction of the sky, and it'll just sit and stare. And it'll stare for about 2 years. And you have to do roughly 2 years because you want to get an Earth-like planet around a sun-like star. Means it's going to be in the habitable zone, the Goldilocks zone, which takes 1 year to orbit. So if you only look for 6 months, a good chance you won't see anything. So you have to look to see the first transit and then see the second transit. So at least 2 years. So I think that very exciting because now we know there's lots and lots of exoplanets. We've seen many of them, but we haven't quite yet seen the Earth twin. And this is one where we're hoping to find the Earth-like twin.
So would the instruments on board be capable of looking at the atmospheres of these planets?
Not so much. So it's more for detecting them. And we'll also look at some other parts. One of the big issues I was telling someone earlier today at the ESA booth is that our sun is a very boring star. And we're very fortunate that our sun is a boring star, because if our sun was a very active star, then we probably wouldn't exist. Because there's so much radiation coming off and coronal mass ejection. So we have to do 2 things to look for an Earth-like planet. You have to make sure the star is benign, so it can't be so active, and then we have to look for the planet. And the combination of 2 is where we want to be.
So Plato is not ESA's first exoplanet hunting mission. In what distinct way will it be different from previous missions?
So we've had a mission which we're partners with the French space agency CNES, and that was called Corot. And that was again looking for these transits. And then we have a small mission operating at the moment called Cheops, and that's a partnership with some of our member states. So it's not an ESA-led mission, but it's a partnership.
Oh, I see.
Yep. Particularly Switzerland and Spain, Sweden are part of that. And again, they're looking for planets, but they're looking more for larger planets near the star. So if you think of if you have a smallish star with a large planet, so maybe 10 times the mass of Jupiter, then the occultation of that planet is quite high. Whereas if you have a small Earth-like planet with the sun, roughly 1 million times different, you're only looking for tiny change. So these are more looking for planets and looking for. Cheops has done phenomenal measurements. So not only can it measure the planet in front of the sun, it can measure the planet behind the sun as well. So it looks for the occultation as well. And a paper came out recently where they found a planet which is rugby ball shaped rather than spherical. And that's, you can get that just looking at the shape of the curve as it passes in front. You can see that it's not quite, there's something changing.
So would that be because the rugby ball shape because of gravitational pull? It's just
because of tidal.
So,
So the triaxial symmetry on it. So and it's because it's very close into the star. So it's not as far as the Earth. You don't really see that, but if you see something very close to its parent star, you can see these things. So it's a wonderful mission providing phenomenal science on exoplanets. And then we do have another mission coming up called Ariel. So Plato is a planet hunter. Just look for it. Ariel is characterization. So we're launching late 20s, and it will be looking for atmospheres. So again, maybe not for an Earth-like star, because you want something where you're getting a good strong signal. We're taking the baby steps in exoplanet science. So, but it will be looking through the atmosphere to try to get signatures from atmospheres of exoplanets.
And that's the next step. I remember when exoplanets were first detected, this whole heap of excitement. Everybody knew that there were planets, but of course there was no evidence. Now we've had evidence for over a quarter of a century. What evidence is there so far for roughly how many are there, how many exoplanets are there, and what sort of numbers do you think are planets which have atmospheres, potentially Earth-like atmospheres?
We've found thousands. I don't actually know the number now, but there was a NASA mission called Kepler, which found, and we normally talk about candidates, because you know once you see something you think is a planet, then you may have to do some follow-up radio velocity measurements to see exactly what is there. But we have thousands of candidates now, thousands of known exoplanets.
And I remember the time when the second and the third, and there was like 100 were discovered. Now you're quite right, thousands, and it doesn't lose count now.
And even just in the release recently from Webb, just last week, I think it was, they showed a spectrum of an exoplanet. I can't remember the name, WASP, one of these planets, and it has water. But not only water, it looks like it could even have clouds. So now you have a planet showing an atmosphere with water in the atmosphere. So I think now with something like, with a combination of Plato finding planets, Ariel will be doing characterization of planets nearby stars, and then Webb, the number of exoplanets is going to go through the roof again. So we're ready for the next massive step. But not only the massive step, but also the step in really probing what are these planets. And
I suspect within, maybe before the end of this decade, there will be detection of exoplanets with atmospheres, where perhaps in a decade's time they'll be planning missions, who knows, maybe going to visit those planets.
I think it's a very nearby one, but space is big.
It's very big.
So even the closest star, Proxima Centauri, it's about 4 light years away. And we know there's planets around Proxima Centauri. But again, if you're to go there with standard means, you're 30,000 years to get there. So it takes a long time. We're looking at some things that can maybe go faster, but they can't really have any information, we can't be transmitting back signals. So
well, I'm going to put something in the calendar so we can have a chat.
I'll be happy to do so.
So what can you say about ExoMars?
Not so much. It was very close. This was a partnership with our Russian colleagues, and it has been ongoing for a while. So the ExoMars came as 2 flavors. There was a trace gas orbiter, which is basically the first satellite that launched. It was going to be looking at the atmosphere of Mars, but also have the relay system. And then the second part of that was the rover, the Rosalind Franklin rover. The rover has been delayed. It was about to launch. It was within, even some of the engineers I know within the European Space Technology Centre, I work in ESTEC, they had already packed up their box. They said you have a box which you send to the satellite, then it gets shipped out with the satellite, so when you arrive all your stuff is there. They'd packed their boxes, they'd shipped their boxes off, and then, as you know, global political situations happened and Russia invaded Ukraine, and that all ended. So the current situation is that we will not be launching this year, obviously, and we're now no longer working with Russia on the mission, but we will be looking at working with our US colleagues to see if we can come up with a way to bring the rover onto the surface. And we're hoping that could be certainly not this year, 24, so you can only launch every roughly 2 years to go to Mars because of the orbital dynamics. Maybe 26 or 28, there's an option.
So it's not all over yet.
No.
Currently, the rover, Rosalind Franklin as it was called, where is it at the moment, do you know?
That's a good question. I think it's in Italy at the moment.
Right, so it's in Europe?
It's in Europe, yes, it's in Europe, it's definitely Europe. And that is, the rover is, it will be fine up to the 2030s. So there's no issue with the fact that it's sitting on the ground just now. It will be kept. One of the big issues, we have to keep it in a very clean environment, because what we don't want to do, because it's taking samples, it's looking for things, maybe microbial life or signs of microbial life. The one thing we don't want to do is contaminate the surface. So one of the hardest things we have with something like the rover is it has to be kept biologically clean.
And of course, being in a safe environment, clean environment on Earth, even when it's not doing anything, does mean that it's relatively safe and you can replace bits that might need replacing prior to a launch, even if that launch is several years from now.
So anything which we feel could be needing refurbished will be refurbished before that. But the thing that the rover itself is certainly qualified until the 30s.
I'm sure this is a huge disappointment for all the scientists and engineers who've been working on this, but the mission is not over yet. And I remember seeing the ESA director Ashbacher on Hard Talk BBC program saying,
I saw that also.
It's not over yet, it's still in the...
Absolutely, no, we're doing everything possible to get it up there. It's so important to have the European rover on Mars, because the science is going to produce that we really want to have it there.
But I still can't help feeling for the ESA engineers who've been working on it for such a long time. So you've been working for ESA for quite a long time now. You've seen the evolution of spacecraft and sensors and the kind of results they've been producing. Would you say spacecraft today are more robust in the harsh environment of space than spacecraft of, say, 40, 50 years ago?
Spacecraft today, so in space we're always talking about, when people talk about, oh, it's not rocket science. You know, rocket science has been the creme de la creme of engineering science. We have to, the technology that we launch, we push the bounds of what's possible in space. And everything we do, we're really pushing what is possible. However, we can't use state-of-the-art technology. You know, we could launch an iPhone into space, but it'd probably last 20 minutes before the radiation would kill it, because we don't have the Earth's atmosphere, which protects us from all this radiation which is outside. So we have to use hardware which is very robust to radiation and to particles, you know, cosmic rays hitting it. So it's not really particles, but cosmic rays. So we use older technology. So it's not so much older, but it's more robust. So rather than having very narrow tracks in your semiconductors, we have much wider tracks. So we're talking about processors, fast processors from the European side, is about 400 megahertz. And if you look at processors of today, it's on the ground gigahertz. You know, we're talking about, you know, significantly slower than you can get on the ground. But then again, we don't run Windows or Mac OS, so we don't have to have all the graphics. So we tune all of our software for every satellite is written specifically for that processor and that satellite. And we optimize every clock cycle. So even though it sounds like it's a slow processor, we can do a lot more with that slow processor than you could if it was on your Windows PC.
So the problem with higher spec processing is that you need smaller tracks, and smaller tracks are far less resilient in the environment of space.
Yeah, absolutely. So if you get a single event upset, we call it, this is a particle hitting that, it could hit one track and it could kill the processor very quickly. So we just have to have things which are robust against radiation in particular.
Is it really called single event upset?
Yep, an SEU, a single event upset, which can, and it has happened. We have had missions where we test and test and test on the ground. So, you know, most of the effort on the ground is not building the hardware, it's testing the hardware to make sure that it can survive. First of all, it can survive the first few minutes, first few seconds actually, of the rocket taking off.
Oh, I see.
So that's really the hard part. When you
so
get
that's the vibration and
the sound. So when the rocket fires, you get if you ever watched an Apollo launch, they fill water. That water is not to put out any fires, that's to try to suppress the sound. Otherwise the sound just hits the concrete and goes straight back into the rocket. And then that would be very bad for what's inside. So you have to suppress that.
High-speed vibrations in the very subtle components you have in the payload.
And so we test everything to make sure if you shake it, that survives, but also if you put it through radiation, it survives. So we do a lot of testing to make sure things survive the environment of space. And that's just part of life, that's what we have to do. And if most things survive on the ground, a good chance they survive in space. And if they survive the first short time in space, they survive forever. But we have had cases where we've launched satellites and within the first few weeks, months, again, a single event upset has destroyed part of the satellite. Now, luckily, we always fly redundant systems. So even when that happens, we can, again, very smart engineers take over. They understand what happened. You know, what would you have to do to cause this particular failure? They find out that maybe a memory block somewhere, and so then they can rewrite the software to avoid that ever happening again. And so we've had cases where that's happened. We've rewritten software, changed pointers to memory addresses, and then the satellite has functioned perfectly until the end of its life. And it's things where you say, why did you not test for that on the ground? Well, you can test for almost everything, but there's always something which can get you.
And that's the excitement, really. Bearing in mind how challenging the environment of space can be, and of course on the Earth base, the environment is very difficult to replicate all the variations that a spacecraft might experience. So it's just incredible that so much survives and functions so well for so long.
So we try. We have within ESTEC in the Netherlands where I work, we have the large space simulator. So this is I can't even remember the size, 8 or 12 meters across. I don't know how high it is, but it's about 3 levels high, and it's a vacuum chamber. But it's specific in the sense that we also have a set of lights, you know, which mimic sunlight. And so then we can put the spacecraft, or one side of it sees deep space, so we have cooling, and the other side sees the sun, so we can start to look at all the effects of, you know, the thermal control in the spacecraft. Because one thing, you know, you can't just cool it down very easily. You have to radiate to space. So we have that. We have shaker tables to simulate launches. We can take things to radiation environments. We can take things to magnetic environments. So yeah, we have the facilities within Europe to do all of testing of spacecraft, and we're very successful because all of our spacecraft, most of our, I think all of them work.
So you do subject spacecraft before they get into space. So these might be spacecraft the size of a bus or something in space-like environments in this vacuum chamber that you mentioned. So you remove the air, vary the temperatures.
We turn on the sunlight so it's seeing. So most people don't realise, but if you have a solar panel, one side of a solar panel round about Earth could be 180 degrees, 200 degrees, and the other side could be seen deep space, which is 3 degrees. And so there's a huge thermal gradient sitting there. Okay, it's not 3 because it heats up, but one side is radiating out to a low number. So you have to simulate that, and that's what we do in the spacecraft to ensure that things still operate, because these thermal gradients can create huge problems if you don't account for them.
Just two last things. There's just so many missions, we haven't covered them all. Are there any ones that you think we should mention right now?
So my pet favourite, for obvious reasons, is LISA, because I've worked on LISA for most of my career, and I love this mission for many reasons, but one is because it's new. So we talked earlier about new science coming along. So the field of gravitational waves, it was theoretical in a way you could say up until September 2015, where the LIGO detectors in the US made the first ever detection of a gravitational wave. And at that point it was unbelievable. We just could not believe we'd measured a gravitational wave for the first time. A few short months later, and I'm telling you, it really was a few short months later, and once it had been announced and made more and more, there was an app on your phone which would give you an alert every time a new signal had been detected. And it got to the point where we're sitting, bunch of gravitational wave people having dinner together at some meeting, and you say, oh, there's another one. And it was amazing how quick it went from being the discovery of a decade to routine. And I think that's phenomenal, that this whole field of science opened up. And LISA is, again, when we talk about gravitational waves, we're not very good sometimes as scientists in giving names, with dark matter, black holes, all this kind of stuff. So we just talk about gravitational waves. Whereas in the electromagnetic spectrum, because we've been doing it for many years, we have infrared, visible, UV, X-ray, gamma. We give different names to things. So with LISA, it's looking at the very low frequency gravitational waves. So analogy would be infrared, and LIGO is looking at the high frequency, the X-rays. So even though we say the same name, it's completely different in terms of their frequency. It's about 6 orders of magnitude difference in frequency. Six orders, but factor minimum. So LISA is looking at things which are moving, so orbits. So we're talking about orbits of bodies. So we're talking about supermassive black holes, the black holes at the centre of galaxies, which are then they merge together. They get caught in each other's gravity. They spin round, and eventually they merge. We're talking about something which may be 1,000,000 times the mass of the sun, and the orbit is a few hundred seconds, maybe up to 1,000 seconds. That's terrifying. Whereas in LIGO, they're looking at things which may be tens of times the mass of the sun, down to about a few times the mass of the sun. And they're orbiting in about 1,000th of a second, or maybe a few hundredths of a second, and again, almost travelling at the speed of light. It's phenomenal to think of the energy emitted. So the first LIGO event emitted about 3 solar masses in energy equals mc squared. With LISA, we're talking about 300,000 solar masses we emitted as gravitational energy. It's phenomenal, and this is brand new. We have nothing like it. We don't even know what we're going to see. So we have, we always have theories. We'll see supermassive black holes, we'll see binary stars within our own galaxy, we'll see small black holes plunging into big black holes. It gives you a map of the gravitational field. But every time we've ever had a new window to the universe, we see things we didn't expect. And LIGO is a prime example. LIGO is designed to measure neutron star mergers. And the first few things we measured were black holes. To the point where we're saying we didn't expect these objects to even exist in the universe, let alone measure them. And then suddenly we're measuring all the time. It's almost one a week for getting these things. I think, why are there so many of these things in the universe? So you have to get all these new theories to try and explain where do they come from. Is it stars that collapsed? Is it a massive star with 2 cores that's collapsed? Is it, who knows? And LISA will be the same. When we launch this thing, hopefully we'll see the things we expect to see, but it's all the other things which really get us excited, because we just don't know what's out there.
It's just like when the advent of radio astronomy, and now you're using these gravitational waves, which you're professor many years ago told you didn't exist, to actually use that as a tool, as an instrument to investigate the
Yeah, absolutely. We're now starting astrophysics. And before it was discovery. Discovery's gone. So we used to talk about gravitational wave detectors, because it was you wanted to detect the gravitational wave. And now we have gravitational wave observatories. Like, it's no longer the detection is gone. It's now we're doing astrophysics for these objects. So it really is exciting stuff. With great stuff happening.
A bit like the black holes. There was a time when they were speculative. Now we know them. Taken pictures quite recently. The idea of what James Webb is doing, imaging or analysing the spectra of atmospheres of exoplanets. It's incredible this to do.
And also James Webb looking at stars, the first stars in the universe. I think that's phenomenal, that we can actually see objects going back 13 point something billion light years. It's just amazing. So everyone says science is over. Science is not over. We're just, every time we do something else, we just open a whole new chapter, and it's just keeps us excited.
You mentioned earlier NASA EYES and the huge resources available from ESA from the Copernicus program. Are there other resources that are available to people who might be interested in aspects of the stuff we've been talking about?
Do you mean in terms of?
For teachers, for students, what resources are available?
Yeah, so for teachers, every year within ESA we run teacher workshops. So we bring teachers from all over Europe to come in to learn, to speak to people like myself, but just to learn about what's happening, what are the projects doing, where's the new science. And I love doing it. I think it's very nice just to speak to teachers. This week at this meeting, the really phenomenal group of people, the volunteers, have really kept this whole organized. This is a big meeting, 2,000 people or so at it, and the volunteers done a great job of putting us all where we're supposed to be. But we have a booth here with ESA, so we're a bunch of scientists just to talk, to explain what is ESA. And we've had so much interest from undergraduate students who are doing the volunteers, just to learn more, how can they get information. So what programs do we offer, internships, young graduate trainees, research fellows. So that's more from the science side. Then we have an open day every year within ESTEC. We normally have, I think, about 8,000 to 12,000 people come through.
8,000 to 12,000
just to see what we're doing within there, and it's wonderful. Again, we get people flying in just to learn about what we're doing in space. So we're very privileged that I work in an environment where I'm excited by it, but I can also get other people excited by it. And so there's an ESA education program, which is you can fly your thesis, for example. We've got the parabolic flights, and again a lot of teacher workshops. So I recommend anyone to go to the www.esa.int, and that has all the information is there.
Paul McNamara, that's terrific. Thank you very much indeed.
Thank you.